Hello! I'm Professor Von Schmohawk, and welcome to YU. In the last several lectures, we studied systems of 2 linear equations in 2 variables, and systems of 3 linear equations in 3 variables. And we have seen how these systems can be solved using the methods of substitution or elimination. Although these methods can be used for systems with any number of variables or equations, as the number of variables and equations increases, the systems become much more difficult to solve. Because of this, mathematicians have devised methods of solving systems of linear equations using matrices, along with a series of operations which can be performed on these matrices to solve a system, regardless of the number of equations and variables. Another special type of matrix which is useful for solving systems of linear equations is an augmented matrix. As we mentioned in the beginning of this lecture, augmented matrices are used to represent systems of linear equations in a compact, easy-to-manipulate form. Augmented matrices are like other matrices with the addition of a vertical line and an additional column of entries to the right of that line. Each row of the augmented matrix is a shorthand representation of one equation of the system. The columns to the left of the vertical line contain the variable coefficients for each equation. Any variable without a coefficient is considered to have an implied coefficient of 1. And any variable in the system which is missing from an equation has an implied coefficient of 0. The entries in the column to the right of the vertical line correspond to the constants on the right side of each equation. We can think of the vertical line in the augmented matrix as corresponding to the equal signs in the equations. Now let's look at a few examples of systems of linear equations and see how to create their augmented matrix representations. When creating an augmented matrix for a system of equations, remember to first make sure that the equations are in standard form, with the variable terms on the left side of the equal sign and the constant terms on the right. The variable terms should appear with the variables in alphabetical order, going from left to right. And remember that any variables without coefficients have an implied coefficient of 1. Also remember that any variable in the system which is missing from an equation has an implied coefficient of 0. So for example, if this system of equations in 3 variables contained any equations with less than 3 variables, then the equations might appear like this. Before creating the augmented matrix, you may find it helpful to create a table of variable coefficients. Placing the coefficients for each variable, including any missing variables, in the proper rows and columns of the table. So let's start by creating an augmented matrix for a system of 2 linear equations in 2 variables. To create the augmented matrix for this system, we first collect all the coefficients and constants for each equation. Since in the second equation x has no coefficient, its implied coefficient is 1. We then collect the coefficients and constants for each equation and enclose them in brackets with a vertical line separating the coefficients from the constants. To create an augmented matrix for this system of two linear equations in three variables, we start by filling in the implied coefficient of 1 for the x term in the second equation. We then collect the coefficients and constants and enclose them in brackets with a vertical line separating the coefficients from the constants. To create an augmented matrix for this system of three linear equations in three variables, we must fill in the implied coefficients of 1 for the terms with no coefficients, and the implied coefficient of 0 for the missing z term in the third equation. We can then collect the coefficients and constants and enclose them in brackets with a vertical line. Likewise, to create an augmented matrix for this system of four linear equations in four variables, we fill in the coefficients of 1 and any missing terms, collect the coefficients and constants, and enclose them in brackets with a vertical line. As a final example, we will create an augmented matrix for this system of 5 linear equations in 4 variables. We once again fill in the coefficients of 1 and the missing terms, collect coefficients and constants, and create the augmented matrix. So far, we have seen how to represent systems of linear equations using augmented matrices. In the next lecture, we will introduce 3 matrix operations called elementary row operations, which are used to transform an augmented matrix to a matrix representing an equivalent system of simpler equations which indicate the solution set of the system.